4.7 Counting problems. Explore. There are 5 swimmers at the first heat of the race. Aubrey, Betts, Cam, Diana, and Elena. How many ways can the 5 swimmers finish first, second, and third? So in this example, does the order matter? Yeah, so order does matter, which makes this a permutation. So we have 5 people, and we're picking 3 of them to finish first, second, and third in a race. So it does matter because finishing first versus finishing second are different. So 5p3 is 10 different ways that they could finish first, second. Okay, so we've already made a mistake. 5p3 is actually 60. How many ways can the 5 swimmers qualify for the final race if the top 3 finishers qualify? So in qualifying, does your order matter? Not technically, no. So we've got 5 swimmers now, so order doesn't matter. Which means we need to use a combination. So 5 choose 3 is there are 10 different arrangements of who could be in the final. So investigate. A band has recorded 3 hit singles over its career. One of the hits went platinum. The band members selected 15 songs, including the 3 hits from the set for their upcoming concert. How many possible sequences for the set list are there if the band wants to open with a hit, play a hit in the middle, and then end with their platinum hit? So does the order of the songs matter? Yes, it does, because that's exactly what we're doing, is we're ordering the songs. Are there any conditions that have to be met? Yeah, we need the platinum in the 15th. And we need to have other hits in the 1st and the 8th. So how many platinum hit songs are there to choose from? 1. There's only 1 platinum hit song. So then how many hit songs are there to choose from for the song in the, this should say, so we've got 1 at the end, 2 options for the middle, and 1 option for the beginning. How many ways can they arrange the remaining songs around their hits? So there's how many spots left? 12. Good. So there's 12 left, and the order does matter. So that means 12p12 for the rest of the remaining songs, because the order matters. So 958,003,200 ways. Another mistake. This is what it should be. So now let's write an expression that represents the number to put this all together. So in the first position, there was 2 C1 options. In the middle position, there was 1 C1 option. And at the end position, there was 1 C1 option. And then for all the other spots, there were 12p12 options. So multiplying all of these together would get you your total. So example 1 says a piano teacher and her students are having a group photo taken. There are 3 boys, 5 girls, and 1 teacher. The photographer wants the boys to sit together and the girls to sit together for one of the poses. How many ways can the students and teachers sit in a row of 9 chairs for this pose? So let's say we have teacher, girls, boys. There's 1 teacher. There's 3 different girls that could be actually arranged in 3 factorial ways. So those 3 girls could be switched around within that group. And then there's 5, oh, sorry, that's girl, or that's boys, sorry. And then there's 5 factorial girls that could be arranged in a bunch of different ways also. But now these 3 positions could also be mixed up, right? We could have the girls here, the boys here, and the teacher there. We could have the teacher in the middle, the boys on one side, the girls on the other. So that's another 3 factorial ways of organizing things. So if we multiply these all together, 1 times 3 factorial times 5 factorial, those are the students, but then they can be arranged in another 3 factorial ways, which will give you 4,320 different ways. Suppose there is a set of 10 different data items represented by A, B, C, D, E, F, G, H, I, J to be placed in 4 different memory cells on a computer. Only 3 items are to be placed in the first cell, 4 in the second cell, and 2 in the third cell, and 1 in the last cell. How many ways can they be placed in the 4 memory cells? So we have 4 memory cells, and the order within the cell does not matter. We're just putting items in there. It does not matter the order that they're in that cell with. So for this one, how many options are there to choose from? How many different things do we have? Nope. 10. We've got 10 different things. And is this going to be a combination or a permutation within that cell? Because the order doesn't matter. And how many are we choosing for this cell? 3. Okay, so then for the next cell, we've got only 7 items left because 3 are already put in there. And we need to pick 4 data items for the second. Then there's only 3 left, and we're picking 2 of them. And then there's only one option, oops, put that backwards, one option left for the last one. And if we multiply these all together, that'll give us our total number of ways. And your answer should have been 12,600. Example 3, how many different 5-card hands that contain at most 1 black card can be dealt to one person from a standard deck of playing cards? So we've got 2 cases here. Case 1 is where you'd have 1 black card, 4 red cards. So 1 black and 4 red. Case 2 is where you'd have 0 black and 5 red. So in this case, we've got 26 cards and we're choosing one of them for the black section. And we've got 26 red cards and we're choosing 4 of them. When we multiply those 2 options together, we get 388,700. Case 2, we've got 0 black cards. So we've got 26 total black cards, but we're choosing 0 of them. And we've got 26 red cards and we're choosing 5 of them to get a total of 65,780. Then to find out the total ways, we add the 2 up to get our total.